Okay, and okay, now for equations quadratic in form, okay, without giving a very long definition, we say that for equations quadratic in form, we say that we have equations where they will not always be displayed as such, but we have equations where if there are two variable terms, say if there are two terms in the dependent variable, but you might have like other categories like differences of squares where you would not have two terms in the variable. But if there are two terms in the dependent variable, then the higher order term will be twice the degree of the lower order term. Now place emphasis on this in case you have twice the degree. And just as samples of equations that are quadratic in form. Okay, now not looking at solving, but just in terms of just showing how an equation can be quadratic in form. And we can say that we have, first of all, we can say that we have x to the fourth plus 19x squared plus 1 is equal to 0. So you have x to the fourth plus 19x squared plus 1 is equal to 0. And we have two terms in the variable x. Okay, higher order, we have it 4. Lower order, we have it 2. And guess what? We have a 4 to 2 ratio. 4 over 2 is equal to 2. And we can say that this equation is going to be quadratic in x squared. In other words, quadratic in the lower order variable factor. And if we have, let's say, something like 3x to the sixth minus 97 x cubed plus 4 is equal to 0. Okay, if you notice between the higher and the lower order terms in x, okay, we have higher order is at 6, lower order we have at 3. Again, the higher order in x is twice the degree of what we have in the lower. So you have a 2 to 1 ratio. And this equation is going to be said to be quadratic in x cubed and let's say that if we have another situation, and we'll say that we have, say, a 5x minus the square root of x plus 88 is equal to 0. Okay, now we have 5x minus the square root of x plus 88 is equal to 0. And another way you could express this, remember, you have 5x. Now the square root of x, remember, with square roots, okay, the hidden index number is going to be 2. So you have like the second root of x to the first. So as a non-integer exponent, okay, the square root of x is going to be x to the 1/2. And guess what? Comparing the degrees, so 5x, you have x to be a first order. And we have 1 to 1/2. And guess what? 1 divided by 1/2. That's going to come out to a 2 to 1 ratio, which is going to go to 2. And this particular case, you're going to have to be quadratic. And the square root of x, or x to the 1/2. Right. So these are just samples of equations that are quadratic in form. Okay, so you have, remember, nth root of a to the m goes hand in hand with a to the m over n. Okay, so if I have like the square root of x, it's like the second root of x to the first. So you have like x to the 1 over 2. That's where that comes in. Yeah, so with square roots, you don't typically see the index number in many publications. So square root of x, you have like this second root of x to the first, like n is at 2, m is at 1, and then translating in terms of a non-integer exponent, whereupon we have a to the m over n. This is going to be x to the 1 over 2. Right. Now, where we have just crossing over, say if we're looking at solving for x, in the case of equations that are quadratic in form, and we'll say that we have x to the 4th plus 3x squared minus 4 is equal to 0. So this particular equation, again, okay, just like the first example, you had to be quadratic in x squared. Okay, so for x to the 4th, now we can factor this. Okay, just like x times x goes to x squared, well, we're going to have x squared times x squared will go to x to the 4th. And for factors of -4 whose sum or difference will be on the plus side at 3. So here we're going to have a plus 4 and a minus 1. Okay. Now, we can start factoring. Okay, now x squared plus 4. Now, a sum of squares cannot be factored. Now, with x squared minus 1, it's your option whether to factor it or not. But for x squared minus 1, this is a difference of perfect squares, so that one can be factored to x plus and x minus 1. And with using the zero product property, okay, so if I set each of the factors to 0, so if I have x squared plus 4 equal to 0, and I look at isolating the x squared term, so we have the x squared is equal to -4, and with the square root property of equality, so if I go from x squared to x, we have equal to plus or minus, okay, the square roots of -4, and in compact terms, okay, so x will be plus or minus the square root of -4, so the square root of -4 becomes 2i, so you have positive and negative 2i for this set, and for the other factors we have an x with x plus 1 and x minus 1. If I set equal to 0, okay, so if I set x plus 1 equal to 0, okay, so I have the x is equal to -1, and for x minus 1 equal to 0, I'm going to have the x is equal to 1, And so we have for our solutions in x, okay, so we have, again, so we have 2i, negative 2i, and we have negative and positive 1. Okay, so you have two complex solutions with 2i and negative 2i, and two real values in the solutions with negative and positive 1. And let me mention here for what we had here with x to the fourth. Okay, now especially if the equation is a conditional, with the degree of the variable being 4, this means you could have possibly have 4 solutions, and we did in this case with 2i, negative 2i, as well as negative and positive 1. Now, another case of an equation quadratic in form, but that has only one variable term, and I'm just going to keep this in fourth degree, and we'll say we have x to the fourth minus 81 is equal to 0. Okay, so in the higher degree in the variable, okay, x to the fourth minus 81, this in its own capacity is a difference of squares. Okay, because here we have x to the fourth would be like the square of x squared, 81 is the square of 9. And so I could factor what I have here to x squared plus 9 and x squared minus 9. Okay, and now I'm just going to mention now, okay, notice I could not factor x squared plus 4, but I could x squared minus 1. I'm just going to mention, okay, so with sum of squares, this one is not factorable. And in terms of what we have with x squared minus 9, because we have a difference of squares, that one is factorable to like x plus and x minus 3. But what I'm going to do here in the follow through is that I'm just going to apply the square root property of equality for both sets of terms. Okay, so if I go ahead and set both of these equal to 0, so I have x squared plus 9 is equal to 0, and I have x squared minus 9 is equal to 0. And if I isolate, okay, the x squared terms, okay, so for x squared plus 9 is equal to 0. If I take 9 away from both sides, so we have the x squared is equal to negative 9. And we have with the square root property of equality, so we have x equal to plus or minus the square root of negative 9. And so in this case, we have x will be equal to plus or minus 3i. And if I, instead of factoring, if I just went ahead and set x squared minus 9 equal to 0, okay, so I can isolate the x squared term upon adding 9 to both sides. So we're going to have the x squared is equal to 9. So we have the x equal to plus or minus the square root of 9. So we have x equal to plus or minus 3. Okay. And so we're going to have yet another set of 4 solutions. Okay, so we have, in this case, right, so we have x is equal to negative and positive 3i. And for x, we have positive and negative 3i. So you have another quartet of solutions, 2 from the real number system and 2 from the complex. And tell you what, in looking at solving for x, I'll give you just some cases here, and we'll say we have for the first, okay, if I have let's say, I'm just going to keep these in fourth degree. Say if I have x to the fourth, and I say I have x to the fourth plus 2x squared plus 1 is equal to 0. Then I'll say I have for the next, and we'll have irrational roots in the mix. We'll say we have x to the fourth plus 6x squared minus 16 is equal to 0. And let's say if we have also for fourth degree in x, we'll say we have x to the fourth minus 16 is equal to 0. Okay, tell you what, if we go ahead and look into these equations again, we have all of these are fourth order in x, so we might possibly have 4 solutions, but no guarantees. Okay, now for the first one, we have x to the fourth plus 2x squared plus 1 is equal to 0. And this equation, okay, that is going to be quadratic in x squared. And this trinomial can be factored. And what's going to happen here is that for x to the fourth plus 2x squared plus 1 is equal to 0, this will be a case of a squared trinomial, okay, where this would factor out to x squared plus 1 times itself. Is equal to 0. So x squared plus 1 is going to repeat. So that means that from x, whatever we have from x, it will come exclusively from setting equal to 0 the expression x squared plus 1. Okay, so you have x squared plus 1 is equal to 0. And if I isolate the x squared term, so upon taking 1 away from both sides, okay, so we're going to have the x squared is equal to negative 1. And we have with the square root property of equality, so we have that x is equal to plus or minus the square root of negative 1. And so we're going to have the x is equal to plus or minus I. Okay, and so instead of having 4 solutions, okay, I have only 2 solutions, and both of these are in the complex domain with positive and negative I. Okay, now for the second problem, we have with x to the fourth plus 6x squared minus 16 is equal to 0. And here I can factor x squared plus 6x squared minus 16, okay, to x squared. Okay, so we have a plus 8. We have times the quantity of x squared minus 2. And I have is equal to 0. Okay, so again, 8 times negative 2 is minus 16. And in terms of adding and subtracting, we have an 8 and a negative 2, where we have that positive 6 left standing. Okay, and if I set each of these factors to 0, so if I set x squared plus 8 equal to 0, and I isolate the x squared upon subtracting 8 from both sides. So I'm going to have the x squared is equal to negative 8. And again, utilizing the square root property of equality. So we have the x is equal to plus or minus, okay, the square root of negative 8. And right now we have x equal to plus or minus the square root of 8 times I. And the square root of 8 is not a perfect square value, but it can be reduced. So again, we have the square root of 8. And we have equal to the square root of 4 times the square root of 2. And so for the square root of 8, this will be reduced to 2 times the square root of 2. So for the complex number solution set I have for x, and we'll have plus or minus 2 times the square root of 2 times I. And in the notation, you could have the I, you can't have the I in front of the radical. Okay. All right. Now for what we have in the case of the third item, okay, so we're back to a difference of squares. But we have a raised order in x. Once again, we have x to the fourth. Now for x to the fourth minus 16, okay, factoring, we'll have x squared plus and x squared minus 4. Again, I have is equal to 0. Now, from the example before, when I had x squared plus 9 and x squared minus 9, I said x squared plus 9 was not factorable. X squared minus 9 was factorable, but I decided to go ahead and work with the square root property of equality for both. But for what I'm going to do here, okay, now x squared plus 4, that expression cannot be factored into real integer coefficients, but for x squared minus 4, I think I'll go ahead and factor this one. So you have x plus and x minus 2. And if I set each of the expressions to 0, okay, so we have x squared, so I have x squared plus 4 is equal to 0. And if I take 4 away from both sides, so we have x squared equal to negative 4. And going from x squared to x, so we have plus or minus, okay, the square root of negative 4. So we have x at plus or minus 2i. And for x plus 2 and x minus 2 equal to 0, okay, so if I respectively take 2 away from both sides and adding 2 to both sides, for x plus 2, okay, so we have the x is equal to negative 2. And for x minus 2, and we'll have the x is equal to 2. So I have x equal to 2i, negative 2i, as well as negative and positive 2. Yeah, so in this one, okay, we have a fourth order equation, okay, that again is going to land at 4 solutions. And before I get too far ahead, I just have to notice, yeah, for x squared minus 2 equal to 0, so you have x squared minus 2 is equal to 0. And if I add 2 to both sides, so we have that x squared is equal to 2. And we have with the square root property of equality. Okay, so you have that x is going to be plus or minus the square root of 2. Okay, so we're going to have, taking what we have now, I overlooked that. So you have for x, okay, so for x squared equal to 2, you have x equal to plus or minus the square root of 2. Yeah. So you have the square root of 2 as well as the negative of the square root of 2. Okay, these are kind of bring us back to those equations that have non-integer exponents. And we have, say, in number 92, okay, we have an equation in D, whereupon we have 3 times D to the 2/3 minus D to the 1/3, okay, and we have minus 4 is equal to 0. And if you notice, you have a 2-to-1 ratio between D to the 2/3 and D to the 1/3. So we can say that this equation is going to be quadratic in D to the 1/3. And just in terms of factoring, let me give you just kind of an analog to this. If I have something like 3x squared minus x minus 4 equal to 0, with the factorization, okay, so I have like 3x squared, 3 is a prime number, 3x squared will factor out to 3x and x. And then for the factors of negative 4, that will allow both the outside and the inside products in the FOIL to add up to negative 1x. Okay, so the factors of negative 4, there has to be a one right combination, whether it's plus 1 minus 4, plus 4 minus 1, plus 2 minus 2, minus 2 plus 2. There has to be that right combination where the outside and the inside products will add up to minus 1x. And the only combination here will be plus 1 and minus, let's see, no, think about another set. Okay, so that is going to be minus 4 and plus 1. So you have 3x squared plus 3x minus 4x gets us to negative x. And negative 4 times 1 is negative 4. Now, instead of x or x squared, I have d to the 1/3 and 3d to the 2/3. And if I apply the same coefficient treatments over here, okay, so instead of x's, I'm going to have d's to the 1/3. So I have 3d to the 1/3 minus 4. And we have times the quantity of d to the 1/3 plus 1. Okay. All right. So just think of like d to the 2/3 is to x squared, is d to the 1/3 is to x, and just factoring. So these are analogous to each other. Now, with these factors, I can utilize the zero product property and set each of the factors to 0. So we have in the first, I have 3d to the 1/3 minus 4 is equal to 0. Along with setting d to the 1/3 plus 1 equal to 0. And if I isolate the d to the 1/3 terms, so we have adding 4, say in the first case, and here we're going to have 3d to the 1/3 is equal to 4. And if I isolate d to the 1/3, so we have upon division by 3, so we have d to the 1/3 is equal to 4/3. Now for d to the 1/3, okay, if I translate from exponent to radical, so d to the 1/3 is going to be the cubic root of d. And we have that the cubic root of d is equal to 4/3. And if I take the cube of both sides in order to translate from the cubic root of d to d itself, okay, so the cubic root of d to the third, so this will become d. And 4/3 cubed, you got 4/3 times itself, and this will be 64/27. Okay. Now for d to the 1/3 plus 1 is equal to 0 for this factor. If I take 1 away from both sides, okay, so I have d to the 1/3 equal to -1, and if I translate into a radical, so d to the 1/3 is like the third root of d to the first, so I have the cubic root of d is equal to -1. Now if I had an even root, like square root or fourth root, I would have no solution, but in the case of an odd root expression can reduce to a negative constant. So I can continue, and we have, upon cubing both sides, we're going to have that d is equal to -1. So for this particular equation, okay, there'll be two solutions, one at positive 64/27 and the other at -1. All right. Now, in taking what we have with 94, so you have another set of fractional exponents. Okay, so I have n to the 1/2 plus 6 times n to the 1/4 minus 16 is equal to 0. Notice between 1/2 and 1/4, 1/2 is like 2/4, which will be twice the degree of 1/4. So this equation is going to be quadratic in n to the 1/4. And just on a parallel note, okay, so if I have like the trinomial, say I have x squared plus 6x minus 16. You know, have factoring, so I have like x plus 8 and x minus 2. Okay, and we say that x squared correlates with n to the 1/2 and x correlates with n to the 1/4. So just kind of analogous to this factorization, but in the case of what we have for the degrees in n. So well, just otherwise x plus 8, I would have translated out to n to the 1/4 plus 8, and I have times the quantity of n to the 1/4 minus 2 is equal to 0, and then setting each of these factors to 0. So with these factors, okay, so we're n to the 1/4 plus 8 is equal to 0. If I take 8 away from both sides, so we have the n to the 1/4 is equal to -8. And writing from non-integer exponent to a radical. So we have that the fourth root of n is equal to -8. And if you notice, okay, we now are back to an even root radical. And I'm trying to say that the even root radical, in this case, the fourth root of n is equal to -8. However, since I'm dealing with an even root radical, the principal square root rule is going to kick in, where the even root of an expression cannot reduce to a negative constant. So for this particular portion, okay, there is going to be no solution. Now for n to the 1/4 minus 2 is equal to 0, if I isolate the variable expression, and so we have upon adding 2 to both sides, so I'm going to have n to the 1/4 is equal to 2. And here I'm going to have the 4th root of n is equal to 2. And then freeing up n, okay, so again I can have even root radical to reduce to a positive constant. And here I can follow through and eliminate the radical upon taking both sides and raising to the 4th power. Okay, so we have on the left hand side I have n and 2 to the 4th. They got 2 times itself, times itself, times itself. And so this will come out to 16. So for this equation, there's only one solution, and that is going to be with the number 16. All right, and we will continue looking at equations that are quadratic in form, as well as some that will have integer exponents, others which there will be none. And now, and again, we will get back to those, but for what we have now, and just crossing over to something that is, I guess, kind of an old topic, but we'll kind of segue over to, I guess, a new domain. And this we have right now in inequalities. Again, your inequalities are your statements like, not in the sense of not equal to, but like less than, greater than, less than or equal to, greater than or equal to. And there are types of ways upon which you can express inequalities. And we'll say we have, for instance, okay, if you have an inequality such as x is greater than 2. And if I were to express what I have here in terms of a number line, okay, so we have in the case of x is greater than 2, if I were to display graphically, okay, so for x is greater than 2, okay, now on the graph, now the book has it as parentheses, but in Alex, instead of parentheses, you'd be looking at holes or open circles. Okay, so on the 2, okay, we have an open circle, meaning that because you have a hole or an open circle, 2 is not included in the description. But for x is greater than 2, representing x will be those values to the right of 2. And so I'm going to have an array that is going to go out to the right. Okay, so this would be like the graphical display of what we have for x is greater than 2. And just taking what we have in interval notation, and the interval notation you would have with parentheses and brackets. Okay, so 2 is not included. Anything that is not included among the finite values, you're going to have a parenthesis. And going continuously to the right, so you're going past 6, and going continuously increasing where we have approaching infinity. Now let's say if we have another inequality. And we'll say that we have, in this one, okay, we'll say that we have x is greater than or equal to -1. Okay, so just representing what we have here for x is greater than or equal to -1. Okay, so we have here for -1, the equal sign indicates that -1 is included. So we have a close point on -1, and the rest of the values x will be greater than. So again, you'll have activity going out to the right. Again, we have with interval notation. Okay, we have activity going in the same direction. Now, -1 is included, and this number is going to be in the brackets. Okay, now let's say if we have a little bit of a change up in terms of the direction. And let's say if we have that x is less than 0. Okay, so for x is less than 0, so we're going to have an open circle on 2. And for less than, we're going to have a ray that is going to go out to the left. Now for the interval notation on this one. If we read in order from left to right, so your leftmost you have continuously decreasing. We have approaching -infinity, and then the upper limit you're looking at approaching but not including 0. So the 0 remains in the parenthesis. And let's say that if we have say for the remaining one direction inequality, if I have that x is less than or equal to 5. Okay, so for x is less than or equal to 5. Okay, so equal sign indicates that 5 is going to be included. 5 is going to be a close point, and then for the less than portion, again, we're going to have a ray that is going to go continuously out to the left. And for the interval notation, so again, the leftmost extreme, we have -infinity, and then we have the maximum you have going up to and including the number 5. So 5 is going to be in the brackets. Now, let's say that if we have x to just simply be the set of all real numbers. Okay, so for what this is going to mean is that you're going to have continuous activity from end to end. So you're looking at the irrational numbers, rational numbers, all the fractions, decimals, positives, and negatives, as well as the zeros. So everything is going to be boundless. So for the interval notation, for what we have for the set of all real numbers, To the left, you have going endlessly to negative infinity. To the right, you have going endlessly out to positive infinity. Now, we'll mention, now, you're going to have parentheses around both negative and positive infinity, because think of like the infinities as endless activities. Think of it like an expanding universe. It never theoretically never stops expanding. So just think of like the infinities, negative and positive, being stretched out continuously, so they'll never come to a final resting place. Thus, no brackets in the notation. And let's say that, okay, so we have, again, one direction inequalities in the first four cases, and you have both directions continuously with all real numbers. But let's say that if we have discontinuity with both the lower and the upper limits, and let's say if we have something like a compound inequality where we can state that something like -3 is less than or equal to x, which in turn is going to be less than 4. Okay, so you have -3 is less than or equal to x. Okay, so for -3, now in terms of whether I'm going to have an open circle or a closed point, the equal sign in the descriptive statement where we have -3 is less than or equal to x, this is signaling that -3 is going to be included, so that is going to be a solid point. Now for x is less than 4, notice we do not have an equal sign, so we have on 4, we're going to have an open circle. And then everything in x is going to lie in between. So for what we will have this time around, instead of having an array or a line to run continuously, we want to have a line segment. We're going to have a starting point and essentially stopping threshold. And for the interval notation, okay, so we have going from and including -3, approaching but not quite including 4. So we have, since -3 is included, we're going to have a bracket. Since 4 is excluded, we're going to have a parenthesis. So I guess you can say that the most we have here, so you have starting exactly at -3, and you have going out to like 3.99999, but never exactly getting to 4. Okay, so these are samples of what we have with inequality statements. And for what we have in the case of section R8, okay, we have not only inequalities, but those that will make reference to what we have with absolute value inequalities. And just again, with absolute values. Again, we're pretty fresh off of the absolute value equations. And sort of tying in together what we had with the equations. And again, if we have that k is a non-negative value, and okay, so just again, just tying in what we had with equations. If we have that absolute value of x is equal to k, then x is equal to plus or minus k. So we have two specific values with k and negative k. But if you're looking at a set of values, okay, and let's say that if we have crossing over to the inequalities, and if we have that the absolute value of x is less than k, if the absolute value of x is less than k, then what's going to happen here is that it's going to be kind of like a squeeze plate. Okay, so you have, again, by definition, absolute value is the distance away from 0. And if the distance is less than k number of units from 0, then your values of x will be between negative and positive k, such that negative k is less than x is less than k, and your interval notation would be like parentheses around the negative and positive k. And if we have that the absolute value of x is less than or equal to k, except for the equal sign, you're going to have history by and large repeating itself. So in this case, you're going to have that negative k is less than or equal to x, which in turn is going to be less than or equal to k, and your interval notation would be, say, brackets around negative and positive k. Right. So you have the same, pretty much the same mode of behavior whenever we have the absolute value inequality to have less than or equal to k. But now if we sort of go beyond this particular scope and say we have that the absolute value of x is greater than k, what's going to happen here is that you're going to have sort of branching out two separate modes of activity. If you're increasing the distance away from 0, you're either increasingly negative or increasingly positive. So for what we have here, you're going to have the x is either going to be less than negative k, or it's going to be that x is going to be greater than k. And how would this look in terms of interval notation? Well, what would happen here is that you would have, for less than negative k, you would have like from negative infinity to negative k. And at the other end of the spectrum, you have going past k on out to infinity. And just for this particular symbol here, okay, this is going to refer to a union of sets or elements or intervals. And if we have, let's say, that the absolute value of x is greater than or equal to k, then you're going to have that x is less than or equal to negative k, or x is greater than or equal to k, and the interval notation to have from negative infinity approaching and including negative k. So the negative k is going to be in the brackets, and you got the union with the other, or the upper half set, where we have going from and including positive k, going all the way out to infinity. Okay, so these are the possible cases that exist for what we have here. And let me just give you a couple of cases where we have absolute value inequalities. And let's say if we are looking at determining the interval solutions. And we'll say we have a statement And we'll say that we have the absolute value of x minus 1 is going to be less than or equal to 7. Okay, so you have the absolute value of x minus 1 is less than or equal to 7. Okay, and see what, let me... Okay, so for your cases here, okay, so for the absolute value of x minus 1 is less than or equal to 7, so you have the absolute value term by itself and the constant on the other. Now k is at 7. 7 is non-negative. And the absolute value of x, again, we have represented by the absolute value of x minus 1. And in terms of how these quantities relate, okay, this statement, this is going to apply for the third case. Okay, so looking at solving for x, okay, so I have the absolute value of x minus 1 is less than or equal to 7. Again, your k value is at 7. So if this is true, then what's going to happen with x minus 1, once you take out of the absolute value notation, it will be sandwiched between negative and positive k, or in this case, between negative and positive 7. So we have that negative 7 is going to be less than or equal to x minus 1 which in turn is going to be less than or equal to 7. And again, I'm still looking at solving for x. So to get x by itself, what I'm going to do is I'm going to add 1 to all sections of this compound inequality. So we have negative 7 plus 1. Okay, so this is going to be negative 6. And in turn, we have negative 6 is less than or equal to x. And x in turn is going to be less than or equal to 7 plus 1, which is going to be 8. And if you notice, okay, so we have negative 6 is less than or equal to x is less than or equal to 8. So for the interval solution, okay, for x, okay, we have from and including negative 6 as indicated by the equal sign. So you have negative 6 less than or equal to x. X in turn is less than or equal to 8. So guess what? 8 is also included, and there will be a bracket around this one. Okay, so that would be the interval solution for this particular inequality statement. And if I have, let's say, and I'm just going to keep the absolute value of x minus 1. And if I have that, the absolute value of x minus 1 is greater than 7. So I'm keeping the k value at 7. And this time for the absolute value of x minus 1 is greater than 7. Okay, this will be a case of the absolute value of x is greater than k. And in terms of what to do with x minus 1 once I take it out of the absolute value notation, well, we're going to have these two types of statements to abound. Okay, so x is less than negative k. This will translate out to x minus 1 is less than negative 7. Or it could be where x is greater than k, which would translate out to x minus 1 is greater than 7. So for what we have in the solution sets, if I isolate x in both cases, so I'm adding 1. Okay, so for adding 1 here. Okay, so for x minus 1 is less than negative 7, x is less than negative 7 plus 1, so we have that x is less than negative 6, or it could be at the other end of the spectrum that x is greater than 7 plus 1, and so we're going to have that x is greater than 8. And just taking what we have with these statements, if I display an interval notation, okay, so for x is less than negative 6, so we have going from negative infinity, approaching but not including negative 6. We have or, and just so we have symbolized by the union with the other set, which we have in x is greater than 8, and the interval notation for this second half will be have a parenthesis around 8. Then we have going all the way out to approaching infinity. Okay, and so that would be the interval solution for this particular inequality statement. Okay, and just some items to mention. Okay, again, so that U symbol again refers to the union of intervals or sets.